velocity times the arbitrary infinitesimal interval, so that will cancel out. And I'll get condition that d-dimensional velocity vectors times the gradient of u in the dimensions, which I can explicitly write as j equals 1 to d velocity times the gradient derivative of u evaluated at the point. And transversality now means that this cannot be zero. So in other words, every place on this surface we have a normal vector to the surface, which is given by the gradient of the function that defines the surface. Doesn't have to be unit length, it's just orthogonal for the surface. And as long as the product of these two things is not zero, I'm transverse. So this is a condition of transversality. So section defined by this condition is good as long as the velocity field in the section, which always generically points out of it because it's d plus 1 dimensional. As long as it is has a component which is orthogonal to the surface. So this is non-zero. And we can get a little bit more out of this. We can also get the orientation condition. Every such hypersurface is oriented. It has the normal vector pointing in some direction, as long as there are no inflection points. And so, generically oriented. And orientation condition is that this quantity, d dot gradient of u, the function thing that defines the thing, is strictly larger than zero. Then it's piercing the same way as a hypersurface. So out of that functional definition of hypersurface, you can check where it's a good hypersurface, where it's transverse, and you can check where your crossing is the legal one, which is in one direction, not in the other one.
Okay.
Yeah.
When we have u of x hat plus delta x is equal to 0, yeah, that one.
Yeah, that means that I'm in a surface.
So,
but I don't have to be zero.
Yeah. So yeah, okay. That's exactly
Yeah,
what I was.
it doesn't have to be zero.
So
So it's a test where the neighboring point is in the surface when this is zero.
Yeah.
And it turns out if the neighboring point is on trajectory, it's going to be zero only if the velocity points in the hypersurface and not out of it.
So essentially, we are choosing delta x such that, it's a test on delta x if
Yeah.
you are on the trajectory or no.
Yeah.
So, okay.
So I'm looking at my neighborhood and I'm just finding whether things are transverse.
Okay.
I have one trajectory. I want to find where the neighboring trajectory is pointing the same way. And it's legal as long as my velocity vector is not in the plane.
So, at a given point, you are defining the Poincare section based on like normality, orthogonality with the trajectory at that point, right?
Yeah, so let me write it down as definitions. We'll see where that helps. So now, definition of the Poincare return map is it's a map that takes a point in a section and returns the first return. The next time you use the section in oriented way. And that's defined. These 2 points must satisfy condition they're in the section. That means they're in a section. And they also must satisfy that they're oriented correctly. So you can pierce this hypersurface in between in the wrong direction, but that one you ignore. So the map is the one which gets you moving the same way after one return. So the gradient of this is useful. If you like this, that would be smooth differentiable functions. Must be strictly positive or strictly negative, depending which way you want to move around, but one or the other. So that defines Poincare section. So here is a simple example. This looks very general and God knows all this stuff. In practice, especially if you're working in high-dimensional systems, for example, if you're working in fluid dynamics or some such cardiac dynamics, something that's intrinsically high-dimensional because it's part of the differential equation, then it's very hard to use any other surface than a plane, hyperplane. Hyperplanes are easy, relatively easy. Everything else requires, Newton iterations to be able to compute whether you're in a surface, etc. So they tend to be harder, and they tend to be very, to define a curved manifold in 100,000 dimensions, it's kind of easy. Not easy. So a typical example is to take a plane and I'll call it template. For reasons which will be obvious much later in the semester, but so you pick a point in the state space. And 1 point, and this thing marks that that's a special point. So what this means is that you have big state space, etc., but there is something that's you're interested in, some behavior. So you have state space of all Iraqis, but you want to see Saddam Hussein or something, one particular photograph. So you pick it as a template, and then you compare other things to it when you're in a neighborhood. And the easiest way to define a neighborhood, so in the state space, dealing with dimensions, state space, here is a template point. And one thing you know about this template point is that generically, unless it happens to be equilibrium which has probability 0, almost everything is moving, it has a non-zero velocity. There is a velocity of template point. So then, and you would like to be transverse. So the simplest way to be transverse is to put a hyperplane that's orthogonal. Just the hyperplane that's orthogonal in all its 999,000 dimensions to this one direction, so just the hyperplane. And the formula is very simple. It says that u of x, this guy is in the hyperplane if any point here, x point, is the vector connecting it is orthogonal to this. That's the vector connecting this point to that one. It has to be orthogonal to the velocity. And this being 0 is the definition of your plane section. So that's very easy to implement. So what it means in practice is, you go on a trajectory and you just check the sign whether you're on this side or that side, etc. So it's a very quick computation. What you pay the price you pay is that you're thinking linearly when you do this. You're being lazy, but your manifold that you move on is not linear, it's curved, etc. So there's no way to cover a curved manifold with a plane. That just can't be done. So you will need a number of local sections such that in every neighborhood you have a good representation of the neighborhood. It's nicely transversed, etc. But this is going to fail you. So that's a simple. No, I guess I've forgotten to tell you when it's going to fail you. I'll come back to that. So that's a very simple example. So something that I assume you already know, but maybe you don't know, is that if you have ordinary differential equations that describe motion in a plane, then there is very little in qualitative solutions you can get. You can either get equilibrium, so you have equations and nothing happens, or you can get a compact solution, but that means that the only way it's not supposed to cross itself, it's in a plane and it eats its tail, so it must be topologically a loop. So you get a periodic orbit. Or maybe if it's an infinite plane, you come in and go out. But that's about it. That's all you can do in 2 dimensions. So 2 dimensions are not very interesting. They're very important for modeling of epidemics and God knows what, population dynamics. They're kind of useful models in some cases. So if you took a ChaosBook course, it never really goes beyond 2 dimensions. It's all about bifurcations in 2 dimensions. It's, and there is rich stuff in there. I mean, there are nonlinear oscillators, all kinds of things can happen. But, for us, it's boring. So to get something more interesting, you need 1 more dimension. You should be able to go here, and then you should be able to turn and fold samples. And it turns out 3 dimensions, the moment you have them, generically you see chaotic behavior. You see this arbitrarily high behavior. So the simplest model is due to a very educated German chemist, Slayer. So Slayer, who I know, personally, if you Google him, you'll find lots of stuff on the internet. Not all of it very complimentary, but the Slayer is a classical kind of German. He speaks Greek and Latin, etc. So in constructing this model, he was inspired by Anaxagoras. But rest of us just do the pedestrian version. And what he did is he wrote very simple equations. So here are two in 3 dimensions. So this is a linear equation that we know how to solve. There's another one, also linear. And this is 1 nonlinear term. Now, Slayer wrote this equation down, inspired by Anaxagoras, but looking at a paper by Lorentz from the 60s, from a meteorologist, Lorentz, who is one of the inventors of chaotic dynamics in modern times. And he tried to capture essence of it by thinking about it, being a thinking kind of person. And I won't do it in the lecture, but then I wrote a long thing in the example in the book, which says how he got to it. So he first said in plane, one of the behaviors which are recurrent, the interesting recurrent behavior is running on a circle. So these 2 equations result that look like harmonic oscillator. But then, unit circle, but then, we know that in nonlinear dynamics, other things happen, there's dissipation, etc. So, so he put this term which says that if y is, if A is positive, y is negative, this dissipates, etc. So this deformed it from a circle. And this wasn't interesting enough yet. This is a kind of deformed circle in the plane. Then he said, oh, you can either spiral in or spiral out to infinity, not very interesting. And said, okay, I'll put an extra dimension in this problem that when these guys get big and I don't know what to do with them, this extra dimension will kick me out along the z-axis. And then something will happen here which will put me back to the origin. I'll drop down and I'll do something. So that's the idea of Rosler's model. And it turns out the moment you write one of these things, you might love Bessel functions or hypergeometric G functions, or you might like conformal field theory, you might like lots of things, but you'll never know what this system does unless you run it on a computer. So the first attempts to run these systems on computers, this was realized already in Poincaré times, so more than 120 years ago. The first attempt was done by a Norwegian whose name escapes me. I apologize now to all Norwegians in the audience, who was a man working on Aurora Borealis, the polar lights, which are caused by electrons moving in magnetic field. So you have to simulate electrons. And he had a number of amanuenses, what we call RAs today, amanuenses. And they spent years computing a trajectory of system not much worse than this one. And if you go to Oslo, they made a wire model of this trajectory, how an electron moves in a magnetic field. It's a really short piece of wire for modern ideas. This took decades to do in time of Poincaré, and today you can write a program and simulate it in seconds in Python, and see much more. So even then we knew that that's what we have to do, but 120 years ago we had no option except torturing few amanuenses to produce little short trajectory. And this will never solve problems of plasma physics and celestial dynamics. Today you can run it, so I'll ask you just to run it. Choose Burak, who is waking up at this moment, likes Python, but you can write your program in any language you want as long as you produce a credible simulation of this one. So now what can we do when we are given this kind of equations? How do we understand them? What do we do with it? So the first step, which I mentioned last time, but now I'll make it a little bit more explicit. First thing you do for such system is you find equilibria. Meaning that velocities are zero. So you find x dot, y dot, z dot equals 0, 0, 0. Whenever that happens, your equation changes its nature. So when this is set equal to 0, it's not a differential equation anymore. It's just three algebraic equations. And because there is a nonlinear term, which is quadratic, you'll get some quadratic equation. That one you have to solve numerically, but because you can write square root, etc., you'll feel that that's analytic. But, for any other system, you'll really have to do it numerically. And the other thing that happens in all these dynamical systems, they have some parameters, often embarrassingly many. So, if you were at Dynamics Days conference last week, there are some stunning simulations with zillion parameters having to do with squid neurons and God knows what, most of which we have a hard time fixing. But this model doesn't purport to describe any physics. It just wants you to learn, essential features of chaotic dynamics. So Rosler, by playing on with this computer, found that if he takes these values, he gets an interesting dynamical system. For pedagogical reason, no physics at all. So when you solve these equations for those parameter values, it turns out there are two equilibria. So the way some reason it's convenient to put x this way, y this way, positive x this way. He found that there's an equilibrium very close to zero. Not exactly zero, but you know. So it's 0.007 minus 0.03. So if you don't look carefully, it will look like the origin is an equilibrium, but it's not. It's close by. And then for this parameter value, suddenly the other guy sits someplace very high up. So this one, x plus, is at, let's say, roughly 6 minus 30 plus 30. I mean, these are not correct numbers. We know them, you know, to arbitrarily many digits because it's a square root of something. But basic thing is that there is one equilibrium here, one equilibrium there, and then what? Now, it turns out that what we're supposed to do, but we don't know yet, we're supposed to study the linear stability of this equilibria. That we'll do next week, so I'm not allowed to do it yet. So now we find these two equilibria, and then I don't know what to do with them. So I take a computer. And what you find out is that if you start close to this guy, and that's kind of implicit if you look at the dynamics in the plane here. Take z very small, 0 is very small. You'll find out that this actually, A positive means it's spiraling out because you know the y is growing, etc. So you'll discover that the typical trajectory is spirals out. I can't do this for a very long time. When it gets big enough so that the x component exceeds this c, this 6, this changes sign, and suddenly the thing that used to be stable now becomes unstable. So what it does is it goes around for a while, spirals out, and then it gets kicked up. And when it gets kicked up, then this guy, x, gets unhappy. It gets a strong negative term, so it starts getting small. So it gets pulled in here, and then it does something and it falls down and keeps going around. So that's what you'll see in a simulation. So qualitative behavior is, this seems to be important because you spend lots of time around this equilibrium, but not at it, and just in the, somehow you're organized by it. Then you cannot escape because you get kicked in third dimension. The third dimension is very contracting, so you come back and you keep doing this forever. And this one, this point here, turns out to be important because if you put your initial point on the wrong side of it, the whole thing explodes. So it turns out this point, doesn't participate directly in dynamics, defines something that's called basin boundary. So you have one behavior on this side and another behavior on that side. So both of them are important, but you cannot see that they're important unless you do a numerical simulation. So that's a typical problem in any nonlinear dynamics. You see this, we see this behavior roughly very qualitatively, spiraling, being sent, sometimes being sent back. We see it in palpitations of chicken hearts, or we see it in Navier-Stokes equations, and some people see it in Young-Mills equations and all kinds of equations. So this is pretty generic. And in three-dimensional dynamics, not much more interesting things can happen than that. It's kind of fairly short list in 3 dimensions of how you can fold back and all this. So I tell you, you're supposed to find a Poincare section. Now, why do I tell you this? Because after simulating this for a while, you'll discover that it just keeps retracing something, and it looks complicated, but you don't know anything else about it. And I say, well, if you take a Poincare section, you'll learn a great deal about it. So where could I put a Poincare section? So it's not ever obvious, but in this case, I seem to be circling around z-axis. It's not quite true, but I seem to be circling around z-axis. So if I put my Poincare section plane so it includes z-axis and I turn it around, no matter how I turn it around, it looks like the flow will intersect with it. So this seems to be a good guess, and for this problem, this is good enough. It does the stuff that you need. So what you do is you say, well, here's one rule of the thumb. If you have some kind of spiraling equilibrium neighborhood, it's a good idea to stick a section through it for obvious reasons. It'll cut whatever. Yeah. So you put a half plane here, but you can turn it around. So if I look from the top, if I look just, this is the z-axis, and I look into the x and y plane, I might want to put this hyperplane this way or that way, or that way, or that way. So now when you do that, this whole flow turns out to actually look quite simple. So if you put it here, before it starts getting kicked, it turns out that the intersections seem to lie on a line. They basically seem to lie very close to the xy plane. And when we do this honestly, we'll discover that actually they don't really lie on a line, but what they lie on its thickness is if you, for example, started your trajectory with accuracy of 1 millimeter on this paper and let it run, then this line will be 10 to the minus 14 meters, or it'll be, thousands of a Fermi. So mathematically, this is not a line, this is some kind of set. But for you and me, this is line. Anything that's thinner than subatomic distances, I think we can call it a line. And we'll understand why. We'll compute the width, etc. It's just kind of thing that happens in dynamical systems, that sometimes you have very strong contractions. But if I put this plane, let's say here, this thing is doing something that it goes around and does this, goes around and does this, and goes around, does this, and goes around. Yeah. Then I'll discover that in that plane I'm cutting this stuff here, and I'll get something that looks maybe like that. I'll get some curve, and if this is called A and this is called B, this will be Poincare section A, Poincare section B. And if I put the plane someplace here, I'll find out that this curve starts bending. This intersection, it starts doing something like that. And if I put it here, I'll discover that now it's falling down, it's falling like this. I'll discover that it looks something like that. It's starting to get thin. And then, as I look to the next, what all the trajectories do to the next Poincare section, it actually gets squashed to a line to accuracy of 10 to minus 13. So what you learn from this is Poincaré section is not sacred. Now, as you put different Poincaré sections, you get different pictures. So they teach you something. They tell you that the object that looks complicated is actually rather thin. And that suggests that even though your original problem is three differential equations, three dynamics, you might be able to describe it by some one-dimensional thing, because the object that dynamics lives on is one-dimensional. And that's now obtained by return map. So what's now a return map? The coordinates here are the radius going out and z. So we have Zn plus 1, the next piercing of the Poincaré section, Rn plus 1, as a two-dimensional, two indices, because it's plane mapped into the plane of and Rn. So that's the correct statement. Now we have hard time visualizing two-dimensional map on the two-dimension because we don't know how to draw graphs in 4 dimensions. It's a little bit hard for us. So we can cheat and we can say, well, let me just look what happens in one of these things. So let me just plot what happens in just Rn dimensions. So if I start someplace in this radial direction, in Rn, and I look at, and I come back to the same section where I'll land, such as this coordinate Rn plus 1, it turns out to be very cute. So, if you take this line here, what happens is it gets stretched, it gets folded, it gets squashed, and it gets brought back into a line. And that means that there is some point here in the middle that was the furthest point at some place, So it was in the middle, it becomes new edge of the interval, and the two edges someplace in there. And when you plot this, it'll look something like that. So this is, an approximate return map. It's not correct because it's just 1 to 1 instead of 2 to 2, which is what you really need. But this P of R is kind of cute because it tells you if I start with this interval, it tells you where every point on the interval will end up in one iteration. And so that sort of motivates something that if this was a math course, I would start with it first. It says that if you have a high-dimensional physical system, it still could be possible, first, that's always possible, to reduce differential equation to maps. That's always possible, that's required. But more impressively, it might be possible to isolate some important directions in this Poincaré section and actually produce one-dimensional dynamics. Because what this thing tells you is that if I'm here at time x n, then I'll be here at time x Rn plus 1. Then if I start with this as a starting point, I use it as my new initial point, Rn plus 1. I'll end up maybe here, etc. So I'll get an interesting dynamics which will actually turn out to describe very well what happens in three-dimensional massive flow, but can be described just by one-dimensional means. So, so that's what you get by Poincaré sections. In Poincaré sections, there is this, motion in the time direction, and that's not the important thing. You want to know how neighbors approach and stretch. Poincaré section captures this, and return map can give you a very intuitive understanding of the dynamics. Now, so I don't know, at this point you should start interacting because, last lecture was just blah, 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 but this is, something you can challenge me on.
Sorry, what is Rn?
Rn is the radial distance. So, if I put the plane, it goes through z-axis. The natural coordinates for it are along the z-axis and radial distance. So that's kind of natural if I'm making this section. Instead of x and y, as I'm turning this around, it's a natural section. So, and the return map, this is 2 dimensions, so return map is from 2 dimensions to 2 dimensions. So that's a rule that tells you, if I start any place in this plane where I end up next time. But it turns out when you look at long-time behavior, it actually, all the interesting stuff is on a one-dimensional curve. So now you're, trying to figure out if you're someplace on this curve, where am I when I come back? And that makes the problem really simple.
So when we talk of a return map, do we ever have like an analytical function?
Never.
Okay. In rare cases, or
No, no. Well, I mean, yes, in textbooks,
yeah, at
I'll
least in
take a
textbook
baker's
problems.
map and I'll do some stupid thing, it'll be analytic, but in real life, never, ever, and for good reasons.
I
The
mean,
rule
so-
of dynamical systems is infinite because it's, all functions you can think of parameterized by continuous parameters. And there's no reason whatsoever that anything should ever be analytical, and it never is. So what's beautiful about the course we'll do now is that, all the data, the moment you started computing roots of polynomials, you must realize that there is a notion of exactness that doesn't mean you write some kind of stupid formula. A root of polynomial of order 5 is a numerical root, but we know we can prove that this is exact to any accuracy 1. So the nonlinear dynamics will be all like that. Everything that you care about will always be numerical. However, the theory of how you use it will be, analytical theory in the sense that you put it as a data in some formula and get a result. And the structure of the formula is the zeta functions are, topological, very analytical. But all computations are numerical, and that's our good luck because otherwise Poincaré would have done it already, and we have nothing to do. It's only in dynamics. Yeah, we can only do it today because we can compute. I mean, the whole resurgence of nonlinear dynamics as a branch of physics and chemistry, and etc., it's all due to computers.
So if you have a bunch of
They don't think, but they're very useful tools. Yeah.
if you have a bunch of nonlinear ODEs parameterized, by continuous time, there's very little probability that you will ever find
I think probability is 0.
0. Okay.
Yeah, it's called integrable systems. So there is in a space of all dynamical systems, there are little points, few of them, which are called integrable systems. We are so lucky that Newton was so lucky and Hooke that harmonic oscillator is integrable and Keplerian ellipse is integrable. And they're the same thing, they just change the coordinates. That's about it. So now you can find 100 examples of integral systems today, but they're usually insignificant unless some miracle happens and some soliton is very important or something, but usually not. In celestial dynamics, you're very lucky that our moon is not moon of Jupiter because those guys are chaotic. So if he grew up on that planet, every time you looked at the moon, it would be like casino, playing, the priesthood will not predict anything because it thinks it's going. And just one possible dynamical behavior, our moon is, because of tidal forces, etc., it's going to stabilize by dissipation. But generically, things can go anyway. So I just want to answer the question about the border. So, there is no, known to me at least, a brilliant way of finding Poincare sections. I don't know how to do it. My experience is every problem, we have to look at it and, we look at dynamics and then we find something. And in Japan, very smart people will put a different Poincare section. But as long as we get the same final number, because you have to understand, these tricks of doing calculations eventually produce a number, like the drag or the turbulent flow. And no matter how you orient our Poincare sections, we should get a number. So in quantum field theory, this is called gauge fixing. You have to choose some gauge to do calculation. But when we are done, this is gone. So, I don't know how to do it any better. So, so if you have some Poincare section here, the natural thing is you have some important region of state space. There are things that are happening, that's why I said template. There are things that are happening that you see recurrent, so they seem to be important. You'll pick somebody there by some line of reasoning, and then maybe you'll put the hyperplane, like you did with the template, or maybe you'll put some curved surface there, because you'll find this better. But how do you know that this thing is good? And how far is it good? Because you started in a neighborhood to understand what neighbors do, but you're later, you would like to be able to explain as much of the flow as possible. So every place on Poincare section, there is a gradient of that function. There's a normal field for every point on Poincare section. And we tend to choose our center of our neighborhood as some place where velocity is nicely transfers to the section, maybe even orthogonal, but that's not required, but just, pierces the section. Now what happens is, as I look at neighboring points, I'll find out that maybe they're slanting, so look at them and the angle between them, the hyperplane gets smaller. And then there will be a border. And this actually is just numerical calculation, and there is nothing, it's computable, and this class 2 years ago computed it for some systems. You get that, you find out that actually, right here, so there is a set of points, I put star on them, which belong to the, section border, whatever letter you want to use, which is D minus 2-dimensional. Because, it partitions the space. This P was D minus 1-dimensional. And they're just set, they're defined by very simple requirement, V of X dot the normal vector at a point. That's all. So the normal vector at a point. Equals it. Now, see, this is very static. This only depends on the vector field and the section that I've done. So it doesn't care about dynamics at all. It doesn't care how trajectories evolve. So this is as easy to compute as equilibria in some sense. For equilibria, the same condition, we require all the v's to be 0. Now we require all the v's to be orthogonal to the section surface. And when you start computing it, because the flows are nonlinear, this is some curved surface, even if you use planes to section it this. And what it says is, out here, things are no good. This is not a neighborhood. Because the velocity is probably pointing the other direction because it just went to zero. So it's probably pointing the other direction. So what you'll have to do is you'll have to make charts. But I can't do this. So, you know, almost always. You have to decide what's of interest in state space. You know, am I only looking at southern states, or I'm looking at, you know, South America, whatever. And then I'll have to produce a bunch of charts. So, you know, maybe they'll be flat, like the maps that we use. So there'll be P1 and P1, P2, 3, 4, 5. And then I have a property that in each one of them you stay away from the border. So, you know, when I go from Georgia to Alabama, I just change my map on the state border without having to the position that, you know, my projection is tangential. In that case, I'm very far from it. But so, you know, in practice, you'll always have to do something like that. You'll have to find a bunch of, you have to decide what's important for you in the flow, and then you'll have to partition it by putting a bunch of locally good sections, which you'll have to, you know, and you have to give the rules how they have ridges that chain themselves together, rules what I changed the map. So this is just, you know, standard geometry, but in dynamical systems we have to do that.
Usually they have to,
What?
they have to overlap.
Yeah, yeah, you know, they have to overlap and they have to be both good. So you have to make sure that the overlap is such that when I put the next chart, you know, I put a chart here, my next chart. So this is my P1, that's my P2. There is a ridge. It says I switch from that map to that one, and I do it before I hit the border. But, you know, it's all ugly like hell, and I can't help it. If this was geometry course, I would just say, well, it's simple, I just put little charts, but they never have to do anything. You know, for them, it's just great. For us, it's hell.